Pre-calculus 9.3, day 3. We are looking at geometric series, and series are where you take the terms in a geometric sequence and you add them up. And so the formula that we arrive at for summing a finite number of terms is shown right here. And that's for a finite, when you want a specific number of terms. And so I could write out that S sub n is your first one plus then your second term, which is a sub 1 times r, plus then your next term is a sub 1 r squared, which would be your third term, and et cetera until you get to your general term, a sub 1 r to the n minus 1, to that nth term. Now, how we develop the sum formula for this is we do kind of something interesting. We are going to take this entire expression and multiply both sides by r. So I'm going to have r times s sub n. And when I take this term times r, I'm going to line it up so it actually is going there. So it's lined up underneath its same term from the top line. When I take a sub 1 and multiply by r, I get a sub 1 r squared. And the same thing would happen if I took a sub 1 times r, I would get an the next one would be a sub 1 r cubed. And so we're getting similar looking terms, and the term right before the last one would be a sub 1 r to the n minus 2. And if I take that times r, I get a sub 1 r to the, you add exponents, and n minus 2 plus 1 is n minus 1. So when the term before this is multiplied by r, I end up with this a sub 1 r to the n minus 1, but then I still need to take this last term times r, and that simplifies to a sub 1 times r. So I have all of these that are being added up. But now what we do is we subtract. So I'm going to subtract this expression on both sides, meaning that all of these are going to be treated as negative. And then these start canceling. And so on the left, I have s sub n minus r times s sub n. And on the right-hand side, all of these are canceling except for the first term up here and the very last term, which is a minus a sub 1 r at the end. Then I pull out s sub n on the left, and I pull out a sub 1 on the right. Except for I forgot to put r to the nth here. I don't know what happened to that, sorry. It's kind of important. It's very important. And now when I solve for s sub n, which is the sum of a finite number of terms in a geometric series, I get this a sub 1, 1 minus r to the nth, all over 1 minus r. And by the way, nothing simplifies here. Because of the r to the nth, you can't cancel the 1's or the r's or anything. So this is your formula, and you'll notice that's exactly the formula that we have right here. This is when you are adding up a finite number of terms. 10 terms, 50 terms, 1,000 terms, but it's a finite number of terms. It's n terms. So you have to show use of formulas here. And so in this formula, you're going to need to know a sub 1, and you need to know the common ratio. So when they say find the sum of the first 10 terms here, you need to note a sub 1 is 24, and you find r by taking the second term divided by that first term. So 12 over 24 is 1/2. So substitute into s sub n, a sub 1, 1 minus r to the nth over 1 minus r. And so I want the sum of the first 10, so S sub 10, n is 10. I want the 10 terms. So I have my 24. And then I have 1 minus 1/2 to, well, n is 10, to the 10th. And I'm just going to put this all over 1 minus 1/2. So the 1 minus 1/2 is 1/2. And 24 divided by 1/2, you end up multiplying by 2, is 48. And then you might have to do this in pieces. You're going to need 2 to the 10th. And the exact value of 2 to the 10th is 1,024. And then you have 48 times 1 minus 1 over 1024 would be 1023 over 1024. And then simplify that carefully, and it comes out to 3,069 over 64. Now, in some cases, the sums get so large that we will ask you to approximate to a couple decimal places, but we would like to try to get an exact answer when at all possible to 2 decimal places. This is 47.95. But see if you can put this into your calculator and get out that exact value of 3,069 over 64. And that is the process, and you need to show use of the formula. All right, so this next one, it says find the sum. Well, you need to write out some terms and determine, is it geometric or arithmetic? Obviously, we're right now in a geometric series, but when it comes to the test, it could be arithmetic, it could be geometric. You got to go back and forth. So again, on this one, this should have been a k minus 1. We're using k equals 1, so the variable should agree on that. And so the summation means start with letting k be 1, then let k be 2, then let k be 3, and so on and so forth until you end up at the end with k is 7. But you have to show use of the formula. So you can't just add those all up by hand. You have to show use of the formulas. And so the first term, I get 2 to the 0th, which is 1. The second term, I get 2 to the first, which is 2. The third term, I get 2 squared, which is 4. And I'll just write the last one as 2 to the 7 minus 1. Well, I guess I could write it 2 to the 6th. And so you need to note from here that a sub 1 is 1, and the ratio is your a sub 2 divided by a sub 1, so it's 2 over 1. Your common ratio is 2. From term to term, you're multiplying by term. And since you started at 1 and you ended at 7, the sum of this is going to be the sum of the first 7 terms. So I'm going to write the formula. S sub n is a sub 1, and we typically write this 1 minus r to the nth over 1 minus r, a little different than their format. So S sub 7 is going to be 1 times 1 minus 2 to the 7th over 1 minus 2. So in the denominator, we have a negative 1, so 1 divided by, right, this 1 divided by negative 1 is going to just be a negative times 1 minus 2 to the 7th. And that is, 2 to the 7th is 128. So you get a positive 127. And so you've shown use of the formula, you've identified a sub 1 and r, and that is how you need to show your work. All right. Example 3. In this one, we have what we call the sum of an infinite geometric series. And if you start adding 1/2 over and over and over again, what we find out is that this converges. This is a convergent series to a specific number. Even though you're adding an infinite number of terms, that's what this plus dot, 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 and there's no end in sight. It just keeps going. We are looking for the sum to infinity. That's what we talk about it as. And if I look at my finite sum, my first term here is 1. 1 minus 1/2. And now I'm going to be taking it to infinity all over 1 minus 1/2. So we're developing a formula here. 1/2 to infinity, as when you have 1/2 to infinity, as this gets larger and larger and larger, this value goes to 0. And so you get 1 times 1 minus 0, essentially, and the denominator there is 1/2. And so that whole thing simplifies to just 2. Now, we simplify this formula. Since it's to infinity, we're simplifying that formula. And notice that since it's 1 minus 0, the numerator just becomes your first term. And the denominator is 1 minus r. And so that is the formula for an infinite geometric series. But this is only good when r is between -1 and 1. It has to have that property that when you take the ratio to a large number and that's getting larger and larger, that it goes to 0. If that ratio is bigger than 1, that isn't going to happen. So you only get a converging geometric series when r is between -1 and 1. If r is less than -1 or greater than 1, it won't converge. And so the formula to infinity when r is between -1 and 1 is that a sub 1 over 1 minus r. But you need to remember, it's only for r between -1 and 1. So up here, my a sub 1 is 1. My common ratio, if I take the second term divided by the first term, is 1/2 divided by 1, which is 1/2. R meets the requirements of being between -1 and 1. This doesn't have a term at the end, so it's going to infinity. So the sum to infinity is that a sub 1 over 1 minus r. It is going to be 1 over 1 minus 1/2, which is a sum of 2. So this box talks about it going to infinity. Notice that there's not an upper limit there of a term. And so that sum to infinity, we can use this formula right here. So example 4, when you see that you are going to infinity, then I'm immediately thinking this if I find out that the common ratio is between -1 and 1. So I still need to look at this and write out a few terms. Again, this shouldn't be an n, it should just be k to match the index of summation, so there's a k. But in this case, we're starting with k is 0. So I get 2 3/4 to the 0th, and then I'm going to increment by 1, so 2 times 3/4 to the 1st, 2 times 3/4 squared, but it's going to infinity, so it doesn't end. So if I simplify that first term, well, 3/4 to the 0th is 1. And then I'm just going to write it 2 times 3/4 plus 2 times, I'm going to write it 3/4 squared, so that I can see from term to term I am multiplying by 3/4. So my R value is 3/4, and it checks. It's between -1 and 1. So the sum to infinity here is a specific value. It converges to a specific value. My first term is 2. So my sum to infinity is my first term over 1 minus my R value, which is 2 divided by 1/4, which is 8. When we get to example 5, this is different. This is not to infinity because we are putting a cap on it, and you're going to need to know how to do this. You will be assessed on this. And so I need to use that other formula where we have a sub 1, 1 minus r to the nth, all over 1 minus r, because this is a specific number of terms. So we actually need to figure out how many terms there are so that I can figure out what to substitute for n. I also have to know, is it arithmetic or geometric? Because it could be either. This is my first term, this is my second term, this is my third term, and I'm noticing that if I take 2 times 3, I get 6. If I take 6 times 3, I get 18. If I take 18 times 3, I'm getting 54. So this is a geometric series because we're adding up the terms. And it's geometric where a sub 1 is 2 and that common ratio is 3. So identify that. But I need to know what term number is 13,122. And so for that, I need to use the general term. So this kind of uses a few different formulas. And the general term in a geometric sequence is a sub 1 r to the n minus 1. And I want to know what term number is 13,122. So plug in my a sub 1 of 2. I have r to the n minus 1. Now to solve this, you can't take the 2 times the 3 because the 3 is raised to this n minus 1. You need to isolate the 3 to the n minus 1. So divide by 2. And that is 6,561 is then 3 to the n minus 1. Now this needs to be done algebraically. You need to show work. And when you have a variable as an exponent, to solve that, you use logs. So we'll just take the log base 10 of both sides. This is the work you need to show. And then the property of logs is we can bring that exponent, but make sure it's in parentheses out in front of the log. I'm trying to solve for n, so divide by log 3. And then you're going to need to put that into your calculator and calculate the log of 6,561 divided by log of 3. It comes out to 8. And then add your 1, and n is 9. So this term is a sub 9. It's when n is 9. So we want the sum of the first 9 terms. Notice it only took the 9th term, that's only 9 terms, and you're already at 13,122. So now that I know that n is 9, the sum of the first 9 terms is going to be my first term, 1 minus that common ratio of 3 to the 9th, all over 1 minus 3. And the 2 and the 1 minus 3 is a negative 2, so that's negative. And so then I've got times 1 minus and 3 to the 9th. is 19,683. And so that comes out to a positive 19,682. And that's the sum of the first 9 terms. And then use summation notation to write the sum. So if I use summation, I can say k is 1, and I'm going to go all the way to 9. And I've got my first term, it's just this general term here, 2 times 3 to the, and if I'm using k, this will be to the k minus 1. So I found the sum. I should have said, and find the sum. So I wrote it, summation notation. I needed to know how many terms to add up. That's why we need to find n is 9. You use the general term and start with k equals 1 and go to 9. And there you have summation notation. That represents that sum, and I also found the sum. That's it.